Okay, so welcome everybody to lecture number 3 or lecture number 19, depending on where you are, of the convex analysis or convex optimization course. So today we're going to finish off the worst case analysis for the case of convex and L-smooth functions, and also for the case of convex L-smooth and mu strongly convex functions. So in last lecture we showed that the class of merely convex and Lipschitz continuous functions, so without smoothness, there's the worst case first order method needs about we'll get the error down to 1 over square root of k, roughly up to constant in k iterations. Okay, so and moreover we started to write down the annoying functions for first order methods for convex and L-smooth functions. So, and actually here it is. So here I recall what we need for the lecture today. So the annoying function is on RD. We actually need it indexed by a k. So we have for every k smaller than n or smaller than n minus 1, we have a convex function, and it looks like this. It's L over 4 times, and then we have 1 over 2 times the norm of dkx squared plus the first entry of x. And this dk is an n by n matrix looking like this. It has a k times k plus 1 block in the upper left corner, with minus 1s on the diagonal and 1s below that. So this is in here. So what we already showed is that this function has a unique minimizer, and it looks like that. In the first k entry, it has these entries, which are 1 minus I over k plus 1. So they kind of decay from 1 minus little plus minus 1 a little more, and then but for the last entries it's just 0. So that's the unique minimizer of that function here. We also estimated its norm squared. It's less than k plus 1 over 3. And this is the exact minimum value. If you plug this here into that function, you get this value over here. And we've also seen, just like in the convex and non-smooth example, that if you apply any first order method to this, this function here and start at 0, then at each iteration you only can fill up the next non-zero entry. In the first iteration, because of this guy here, you're going to fill up the first entry with something, and then in the next iteration you're going to fill up maybe the next, and maybe the next, maybe the next, but nothing more. So you know that the kth iterate of any first order method will look like this. It has something in the first k coordinates, but the last n minus k there is still at 0. And this is what we're going to use to show that this is actually really bad. Is a bad function. Yeah? Okay, so and I think now we're already done with all of the preparations, and I can start the main theorem, which already now gives the final result for this class. So this is now then theorem 19.1. And it says, so we have some n given, but we now consider only k up to 1 over 2 n minus 1. And then any x0 in Rn as a starting point. And the claim is that then there exists some f on Rn, convex and L-smooth, such that for any first order method so meaning that in each step we only can get to evaluate the gradient at the current point, and then we can move freely in the span of the previous gradients. It holds that we have that the distance to optimality and functions value for the kth iterate is still not smaller than, and now comes a little bit weird numbers, it's 3 times L times the initial distance to optimum squared over 32 times k plus 1 squared. And there's also a lower bound on the distance of the kth iterate to the solution. So there's an x star here squared. It's larger equal 1 over 8 times the initial distance. So that's the result. So that's the lower bounds we get. It's basically choosing the function like this here up there. But okay, first let's do some interpretation here. So it says that if we, in each dimension, we can find a function f such that which is convex and L smooth, such that when you apply any first order method for k steps, and these k steps should not be more than roughly half of the dimension, then the distance to optimality is still that large at least. And what is more is that we could not decrease the distance to optimality in the axis by more than a factor 1 over 8. There's nothing more than that. Okay, so some remarks which I could also make in the end, but I make them now already. So this only holds for for the first iteration, so not for all of them. And one reason is exactly like before, that if we do n iterations of a first order method, then we span the whole space, possibly. So we can't say we couldn't span the whole space. So the next iterate is not, there's no way of saying or of guaranteeing that the next iterate is not the exact solution. So larger than n it's totally impossible for first order methods. But in this case we only get half of n, a little bit less even than half of n minus 1/2. So it's a little bit less, but anyway, so these results are most interesting in the case where the n is very large, so the n is in the millions or something, so that half of n is still a large number of iterations. So the result does not say that everything holds for all k, not even for k up to n, but only for n over 2. But still, that's still enough, because in many cases it's making number of iterations which is half the dimension is still more than one would like to do. Okay. Okay, and then you may notice that this lower bound here is much better than it has been without smoothness. Without smoothness we've seen 1 over square root of k, and now we have 1 over k squared. It is a much higher exponent, so the exponent moved up from 1 over 2 to 2, so it's 4 times as large. Okay, good. So let's prove that. So first we assume, so without loss of generality, assume x0 to be 0, and if this would not be the case, you could just shift the f by x0, then this would be the case. And then we take f as the function f2k plus 1. So exactly this function from here, but not with k, but with 2k plus 1. And that works because 2k plus 1 is still less than n, and that's still fine what we're doing here. Okay. So then what we know from this here is from the previous results, we get that. So first is what is the function value at the kth iterate. We already know a little bit about that. So so no matter what the first order method produced, that's the kth iterate, and we know it looks like this. So of course this function is now this one with index 2k plus 1. But we've seen, I think it was called Corollary 18.4, that this is exactly the same as this here. Because it kind of only looks and takes a smaller matrix over there, but the difference in the matrix does not lead to any difference in the function value, because the xk only has entries in the first k components. And this is definitely larger than the minimum of fk star. This minimum value this here, actually. This is what I think this is what we called fk star. So this is corollary 18.4, and this is just because this is not guaranteed to be the minimizer, so this is actually maybe smaller. And moreover, we calculated this to be this number here. It's L over 8 minus 1 plus 1 over k plus 1. Okay, so that's basically it, more or less. Now we're almost done with the first claim here. So what do we get? We get now f of x it's k minus f star minus f star k. Yeah, this is okay. Is and divided by the distance to optimality of the initial value. So okay, and this now we can bound that from below. So first we make this guy here smaller by using that value. So it's L over 8 minus 1 plus 1 over k plus 1. And then we have to subtract the minimum value of f, but f now is the one with 2k plus 1 down here. So the minimum value this here is L over 8 minus 1 over, and then for k I have to plug in 2k plus 1, which gives us 2k plus 1 is 2k plus 2. So we estimated this from below, but we took this one exactly. Okay. And this here, the first guy is 0, so this down here is norm squared of the optimizer, of the minimizer. And recall that the norm of the minimizer is bounded from above by k plus 1 over 3. So here, if we bound this from above, we make the fraction smaller, and so it's 1 over 3. And for k, you have to plug in 2k plus 1. So it's 2k plus 2 again. So this is estimated, so we made that larger and we made that smaller, and this was exact. Okay, so now let's collect things here. Yeah, how do we do? Let's let's say you do L over, and then we have 8 times 3, which is 20. Oh no, the 3 goes up top, because it's down it's down here twice. Then we have an 8, and here let's do it like this. And here up there the minus 1 cancels, because we have minus 1 here and the negative minus 1 over there. They cancel out, so we are left with 1 over k plus 1 minus 1 over 2 k plus 1. And if you calculate what comes out here, so yeah, just a little bit of algebra, this gives you, no matter, it gives 3 over L, 3 times L over 32 times k plus 1 squared. Yeah, so this, yeah, that's just how it is. So this up here gives 1/2 times 1 over k plus 1. 1 over k plus 1 goes down here, and get the k plus 1 squared, and then we get 1/2, 1/2, 1/8, which gives 132, 1 over 32. So that is that. And this already shows our first claim, right? If we look here, we multiply this inequality by x0 minus x star, norm squared, and we're exactly here. So this is already the first claim. Okay, for the second, that the distance to optimum is not reduced by more than a factor of 1 over 8. We do as follows. So we want to estimate this distance here, and what we do is, so we know that the first So the first entries in xk may be exact already, so they may be the correct ones. We can't exclude this possibility, but we know that the last entries here are 0, and we know that the last entries here have the specific form we have up there on the paper. So we can estimate from below by just neglecting the first k entries here in the difference and only sum up the squares of the last ones. And the squares of the last ones, they start from k plus 1 and go up to 2k plus 1. And then it's here, so for these entries, the xk doesn't have 0 as an entry, so what we'd have to write down here is only the entries in x star. And the entries in x star, actually there's a typo in the lecture notes. So in the lecture notes I have written here x2k plus 1 I squared, but so this is also, I could have introduced this notation, but what I really mean here is this should be the entries of x star. I think in the previous version of the lecture notes I denoted the minimizer of f2k plus 1 by x2k plus 1 up here, but now I need this 2k plus 1 as the, so what I really wanted to do here was x star I. So only the entries of this. Okay, we know them. This is sum from k plus 1 to 2k plus 1, and the entries are minus 1 plus 1 over, and then we have 2k plus 1, which is 2k plus 1 plus 1, 2k plus 2 squared. So these are the entries of that. Yeah, okay, and so now we need to calculate that sum, and this is now just yeah, basic arithmetic. It's we write that down as sum of k plus 1 to 2k plus 1, and then we just calculate the square. It's 1 minus, oh, this actually is an I, another 1. This is the I, the summation index. So then here we get I over k plus 1 negative, because we have one negative here, plus I squared over 4k plus 1 squared. Okay, and now let's calculate. This amounts to 3 sums. We calculate the 3 sums. So the first, maybe color code them. So what about this here is very simple. The sum of I equals k plus 1 to 2k plus 1 is over 1 is just equal to k plus 1. Is it k plus 1? Yeah. Yes, because it includes the boundaries. So that's simple. What about this one here? So what about the sum over I from k plus 1 to 2k plus 1 just over I? So we have one factor of 1 over k plus 1 in front. Maybe I just put this here. So what do we get? So we write this as the full sum starting from 1 to 2k plus 1 over I minus the sum going from 1 to k. And then we're going to use the famous identity that the sum over I from 1 to k is k times k plus 1 over 2. Use it in both cases here, and we get 1 over k plus 1 from there. And then here, this is that with 2k plus 1 instead of k, and we will get 2k plus 1 times 2k plus 2 over 2. We have to subtract this guy here, k times k plus 1 over 2. And then you see, well, it's, yeah, if you just collect everything together, this gives us 1 over 2 times 3k plus 2. I think that's what should come out here. Yeah. Yeah, that's how it is. I only so in the lecture notes I have here times k plus 1, but I don't did not divide by k plus 1 over here, so that's what's coming out there. Oops. Okay. Okay, so that was that, and then we still have this term here, and this term is, so maybe I just calculate the 1 over I squared. I goes from k plus 1 to 2k plus 1, and here we also use some identity which I'm not going to prove here. If you sum from I to k over I squared, you get k times k plus 1 times 2k plus 1 over 6. So it's not that hard to prove that by induction. Okay, so now again we separate the sum over the I squareds from why there is a difference of 2. One going from 1 to 2k plus 1, one going from 1 to k. And so we have this times this thing here twice. One with 2k plus 1 instead of k. Okay, maybe I should turn that off. I hope that works. Okay, and so this gives a kind of longer expression here, so this guy gets one of these sums. So in the end, what we're going to get is 1 over 6, of course, and the rest amounts to k plus 1 times 2k plus 1, and then times 7k plus 6. So calculating this, it's no magic, but it's tedious. Okay. Okay, good. So what does it give? So, and again, of course, we could pre-multiply by 4 times k plus 1 squared and divide this by this, and then, okay. Let's do that on the next page. So, collecting all the things. So, collecting all the things, we get the distance of xk minus x star, the kth iterate minus the optimum, is bounded from below by, so from the first we get the k plus 1. From the second we have to subtract this guy here. Yeah, it's 3k plus 2 divided by 2, and then we have to add this guy here divided by 4 times k plus 1 squared. So it's kind of it's 1 over 4 k plus 1 squared times k plus 1, 2k plus 1, 7k plus 6 divided by 6. Yeah, okay, it looks a little bit complicated, but anyway, so clearing this up. Yeah, so first, so maybe I skip a few steps because it's really just algebra to calculate these things here. So you can end up with 2k squared plus 7k plus 6 divided by 24 times k plus 1. So that's exact now. This is exact calculation. Okay. And so what we're going to do now is we make things smaller by multiplying by something less than 1. And we're going to, so first I copy this term here, plus 7k plus 6 divided by 24 times k plus 1. And we multiply by something which is less than 1, and this is 3 over 2 times k plus 1 times x0 minus x star squared. And this guy here is actually less or equal to 1. Because of what? Because this here is upper bounded by 2k plus 2 divided by 3. So this is the reason why this is smaller than 1. Okay. Yeah, and so now we're basically done. We just clean up. So for example, you can cancel this 2 here, the 3 with the 24 to 1/8. What actually, this is not what we want to do. Yeah. So this, yeah. So 3 and here cancels to an 8, but there we get a 2 over here, which gives us 1/16. So 16th, and down here we get the k plus 1 squared. And up there we are left with this guy here, and probably, yeah, maybe I just 2k plus 2k squared plus 7k plus 6, and this is here in the end, it's still x0 minus x star. So now what we do is this 2 times k squared plus 7k plus 6, we make it a little bit smaller by reducing it to 2k squared plus 4k plus 2. And why we do that? Because this gives 2 times k squared plus 2k plus 1, which is actually 2k plus 1 squared. So we make this a little bit smaller here, and if you make the same thing here, we can estimate this guy from below by that. The k plus 1 squared cancel, and again, actually we're going to end up with 1/8 times x0 minus x star. And it's 2 norm squared, of course. And that was it. That was the second claim. Okay, it's a bit of a weird calculation, and actually, but the part of this estimate here is probably the weirder one, but it checks out. But the more important claim is probably, if I take a look at the theorem again, the first part here. That it's really like if you are in n dimensions, then for the first n minus 1/2 iterations, you will not get better than this no matter what you do in the worst case. Okay, this was actually a very quick computation. Okay, good. So that's the annoying function here. And these remarks here, I already made them more or less. There's one remark I would like to make still is, so we see that this f of xk minus f star is kind of O of 1/k squared for k goes to infinity. This is, the exponent here is 2. Oh, it's not a nice 2, but this is an exponent is 2. Another way to phrase this is let's write this to guarantee that the distance you get if you apply some first order method to any function, and you want to make sure that you really know that you're less than epsilon away from the optimum, you need at least k more than, and then it's just shifting terms around, square root of 3l over 32 times this something here, oh, this should be up there, the 0, squared over square root of epsilon minus 1 iterations. So this is not really computable because we don't know the distance to optimum, at least somehow. Okay, but anyway, what is now important here is what you see is if you are at some point and are not satisfied with the result and would kind of improve the distance to optimality by a factor of 2. Let's say, so you have been, you're down to epsilon, how much iterations you have to do to get down to epsilon over 2. So you have, if you cut this epsilon here in half, you add a factor of square root of 2 to the right hand side. That's what you had to do. Add a factor. So if you want to cut the error in half, you need to do the square root of 2 as many times iterations as you've done. So if you're with 100 iterations, you had epsilon is equal to 1/10. If you want to get down to 1/20, you need to do about 141 iterations. And this goes on and on. So if you cut it in 2 by cut epsilon in 2 again, you have to multiply by 1.4 something for the number of iterations again. So that's kind of how it scales, right? How it scales, how accuracy and number of iterations scale with each other. And another takeaway is that from this here, the interpretation of this result here is that the iterate, they converge, we can show that, but they do converge arbitrarily slow. There's no, they may converge arbitrarily slow. There's no guarantee you can get that you will be that small after something. So the conversion of the iterate may be arbitrarily small. And again, what is also, yeah, sure, you can't get any better than that because, well, you don't really know that minimizers are unique in this case. You only have convexity and L smoothness, so there may be a convex set of minimizers, so we'll for sure cannot drive this down to 0 for all the iterate, for all the optimal solutions at the same time. Okay, that is the result for convex and L smooth. That's the scaling. You need K has to go up, like 1 over square root of epsilon goes down. Okay, so now let's come to the convex, so the strongly convex and smooth case. So, okay, now mu strongly convex and L smooth. So, how does that work? So, in this case, we know that minimizers are unique by strong convexity. So we may even try to drive down the distance to the minimizer to 0. That's a little bit more than we had hoped for in the just smooth case. And what we do here is, to make things a little bit simpler, we work in infinite dimensions. Infinite. So actually this makes things simpler. May not sound like it, but it does, because then we don't have to worry about the upper bound. So in infinite dimensions is like the set we're going to consider. So the what used to be Rn is going to be replaced by the so-called set L2, which is the set of square summable sequences. So it's the set of all xi, I in n, and the sum of the xi squared is finite. So that's still a vector space. It's kind of infinitely long vectors, and we have the condition that the squares of the entries should form a convergent series. Okay, and it has an inner product. If we have two infinitely long vectors, the inner product is just exactly the same as in Rn. We sum from 1 to infinity over xi times yi, and the corresponding norm is also denoted by 2 norm. Actually, I think in most cases I'm going to omit the 2 down here, but anyway, that's just summing up all the squares. Actually, here's also 1, and then takes the square root. So it's basically the same as Rn, but the only thing is that we need this extra condition that the sum of squares is convergent, so that we can even evaluate the norm. So there should be no elements with infinite norms, so to say. Okay. So this is infinite dimensions, but it doesn't make anything much any simpler. These always, as you'll see, all the series which may appear, they always converge, and it's really not that difficult. So here's the annoying function. So we do two constants. So one is the constant of strong convexity. I just plug it in here, and then I need another constant which I call Q, and I think I just call it Q, and the electron is called QF, but let's just call it Q. It should be larger than 1, and then we define f, which gets indexed by mu and q of x as as mu times q minus 1 over 8 times the first entry of x squared plus, now a series, I goes from 1 to infinity, xi minus xi plus 1 squared minus 2 times xi. Okay, and then plus mu over 2 x squared. Okay, so it looks a little bit like we had before. Actually, it is more or less. The main difference is we have a different constant here. Now we're in infinite dimensions, and we have this guy over here. So we can again write this as mu times q minus 1 over 8 times norm of dx squared minus 2 times inner product of x with ei plus mu over 2 norm x squared. And what is this d? The d is basically as before, but now it's an infinite matrix. So we have minus ones on the diagonal and ones below, but this is going to continue up to infinity. Okay, good. So let's see that this function is bad. Okay, and there's a lot of computations again. Okay, so the computations. So first, it's that by the same arithmetic as for a function in finite dimensions, the second derivative. Oh, and there's still. The second derivative of that guy is again mu times q minus 1 over 8 times d transpose d with the transpose matrix here, but then still plus mu times the identity which comes from here. The second derivative of the squared norm is just the identity, so this goes here. Again, we call this guy a here, and this is also of the same shape as before. It has 2's on the diagonal and one negative ones on the first upper and lower diagonal. And it's also similar to before. You can see that this a is of course positive semi-definite, but it's also bounded by 4 times identity. So what you're going to see is that the second derivative here is you have upper and lower bounds. By replacing these guys here with the lower bounds 0, you get the lower bounds mu times identity, and the upper bound you multiply this by 4. Oh, actually I was wrong. So this 8 is the 8 here is wrong. By taking the derivative, I get a factor of 2, and so we're only left with 4 over here. Okay, so in this 4. We replace this by 4 times identity, and you end up with mu times q minus 1 plus mu times identity, which is exactly mu times q identity. So this shows f is mu strongly convex by this lower inequality, and this upper inequality gives us L smoothness, and L smooth with L is equal to mu times q. Okay, and so then this number q in this context has a name. If you have a mu strongly convex and L smooth function, the number L over mu is called the condition number. And I think you already had that one. So in this case, what we do for the function, we do not prescribe the constant of strong convexity and smoothness, but the constant of strong convexity and the condition number. Okay, so that is now checked. That works. That checks out. But what now about minimizers? So we know. We know by strong convexity that minimizers exist and are unique. So, but what is it? So I formulate this as a lemma. So this function f mu q, no, oops, what did I do here? There's more typos. So the function is actually only this f mu q, has a unique minimizer. So we know that already by strong convexity. Let's call it X star. And this has the entries X star, let's say K. And this is now quite nice because the entries really form a geometric sequence. So the entries are of the form Q to the K, and Q, the small q, is very simple actually. It's the square root of capital Q minus 1 divided by square root of capital Q plus 1. So this is now nice. So the entries in the minimizer form a convergent geometric sequence, like they have. So the first one, so they just go down geometrically fast, because this small q here is that expression, and this is for sure smaller than 1, because what's up here is smaller than what's down there. Okay. So our minimizer is an infinitely long vector, and the vector entries are, the kth entry is q to the k for that number q. Okay, the proof is also just checking. So the optimality conditions is are we can read them off from here. We just multiply by x and set to 0. No, that was wrong. We should have used the gradient actually, right? So optimality condition would be 0 is equal to the gradient of f mu q at x star, and this is then, I didn't calculate the gradient, but it's also straightforward, as mu times q minus 1 over 4 times a plus mu times identity times x star. And then in the first derivative we still have this guy here. So it's still minus mu times q minus 1 over 4, yes, times ei. This would be equal to 0. So that's the optimality condition. Okay. Okay, so what we have to do is, so we didn't just bring this vector to the other side, multiply by 4 and divide by mu times q minus 1, and we're gonna end up with that we need to solve a plus 4 over q minus 1 identity times x star is equal to ei. Okay, let's write down all these equations. So let's write down all the equations for the entries. Okay, so the first equation, if you look at A, so the A was the matrix with the 2's and 1, the minus 1's. So the first equation is 2 plus 4 over q minus 1 times x1 minus x2 is equal to 1. This is k equals 1, first equation, and for the k larger equals 2, we also have one more summand here, which gives minus x k minus 1 plus 2 plus 4 over q minus 1 times xk minus xk plus 1 equals 0. These are all the equations. So for each natural number we have one equation. For k larger than 2 we have all these here. Okay. A little bit reformulation. So for example, calculating this and that. Yeah, probably just we do that once. This guy and also that here evaluates to 2 times q minus 1 divided by q plus 1. Sorry, that was wrong. It's the other way around. 2 times q plus 1 divided by q minus 1. Sorry, it's like that. Okay. Yeah, now you just need to check check that xk equals q to the k with q is square root of q minus 1 over square root of q plus 1 fulfills all equations. It's just checking, it's just plugging in. So one thing which you notice why this is not so difficult is, so if you plug in q to the k over here, and then you get q to the k minus 1 here, q to the k here, and q to the k plus 1 here. Then you can factor out the q to the k minus 1, and then here's just the q to the 0, q to the 1, and q to the 2 is left. So then you only need to show that q fulfills the quadratic equation. And this quadratic equation it has to be one of the two roots of this quadratic equation, and one of the roots is larger than 1, and the other is smaller than 1, and it's exactly that. And it also fulfills the first one. So that's basically it, because this could be then, so this would be q to the 0. So because then this equation is basically of the same type of this. It's q to the 1, q squared, q to the 0, and so on. And so on. Okay. And omit this calculation, it's not really enlightening. Okay, well, on the other hand, we also progressed through the half of the time, so it's probably time for a short break of a few minutes, and then you proceed with the last theorem and its proof. Actually, it's only half of a page to go, so it was quicker than I thought. Okay, so short break, and then I come back. See you then. Okay, here I'm back. Okay, good. So we know that this function, which we hope will be the annoying one, has this minimizer here, which consists of a decaying or geometrically decaying sequence. And so now we just use it and calculate the lower bounds. Yeah. So, and this is just, now we just call it theorem 19.3. So for every, and it's now that formulated in infinite dimensions, but it's not difficult, not more difficult. So for every initial value in L2 and every constant of smoothness and strong convexity, there exists an L smooth and mu strongly convex function f with minimum f star attained at some x star such that the iterates of any first order method fulfills the following: the distance between the kth iterate and the optimum is bounded from below by the value square root of q minus 1. Oh yeah, and of course this q is again L over mu. Square root of q minus 1 divided by square root of q plus 1, and this here to the 2k, and then it still times the initial distance. So here our lower bound is much smaller, because this is a number smaller than 1, and this we raise it to the power 2k, so it goes down exponentially fast. And as before, it goes down like 1 over k squared, and here it goes down like q to the k. So the small q to the k. And the distance to optimality and function value is basically the same bound multiplied by mu over 2. Okay. Okay, so, and this is again more or less only calculations, because we proved just not that many of them, because we proved we did most of them already. So again, without loss of generality, we take x0 to be 0, and also we take this f mu q as before. Then we know this guy here, x0 minus x star, this distance squared. So what is this? Because this is always 0, it's just the sum of the squares of the entries of x star. So yeah, this is just sum from I goes from 1 to infinity xi star squared, and we calculated these guys. It's from 1 to infinity q to the 2k. Yeah, and that's a geometric series without the first term, so it's q squared divided by 1 minus q squared. So it's just geometric series. Okay. So as before, we know that the xk for any first order method is of the form something, 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 and then comes zeros. And these are the first k entries. Right, this is the same thing as before, because the D has this, or the A has this tri-diagonal structure. Only the first upper and first lower diagonal contain non-zeros, and the diagonal, but nothing more. So in each iteration you only can pick up one more entry, as before. So what can we conclude from that? Then we can conclude that this distance here, yeah, we can bound it from below, because by just summing up the last entries in X star. Right? We forget about what happened to the first K entries because they may be exact, they may also be zero, the difference. But for the last entries coming after the kth one, there may be something. There's nothing here, and there is something there. So the lower bound is I sums up from K plus 1 to infinity, and again X star I squared. Same thing. Q to the 2K. And it's again, I don't know, for this I always don't have them in mind, how it works. So it's 1 over 1 minus Q squared. It's a full geometric series, but then we have to subtract the first K, and for the first K we have 1 minus Q to the 2, K plus 1 divided by 1 minus Q squared. Of course, again, this is Q to the 2 times K plus 1 over 1 minus Q squared. But if we compare with this here, that's actually Q to the 2K times X0 minus X star. And that's already it, right? That was it. The difference of the kth iterate to the optimum squared is larger than Q to the 2K times the distance of the initial iterate to the optimum. That was already that. And now so this proves this here. And for that, it's very simple. There we had a lemma 17.4, which shows that f of xk minus f of x star is smaller or equal to, and then we have the inner product. So f of xk minus f of x star is larger or equal to. We have an inner product here with a gradient of f at x star, but that's 0 because x star. So maybe let's write down gradient f of x star, xk minus x star, but plus mu over 2 xk minus x star because of strong convexity. But this here is 0. And then we are basically done because we already know that this here is the same bounded by that, so it's then mu over 2 q to the 2k, and x0 minus x star is the lower bound. And that's it. That was the full proof for that. And I think that's what we wanted to do today. So let's recap, because it was a lot of material. Actually, it was not that much material, but a lot of computations. So in case somebody got lost in the details, actually there are two main results today here. Okay, so maybe I just recap the two main results. So the first main result is in the class of convex and L-smooth functions, there is a function such that any first order method does not do better than this in the first iterates. But so if you just omit this above here, they say that okay, the error in convex optimization with first order method cannot go down faster than 1 over k squared. Okay, without okay. And also the distance to optimality does not really decay by more than a constant factor independent of the dimension. So the good thing here is that all this stuff here is independent of n. So n is the surrounding dimension, it's all independent of that. Or it depends on this only that it holds for the first n over 2 iterations, but there's no like this is here depending on n, so the larger the problem, the more difficult it gets, or the smaller. So that's a good thing about convex optimization. All these constant here does not depend on the space dimension. But the bad thing is that this goes not down any faster than 1 over k squared, and this just don't go down by a constant factor, and that's it. So then there was all these calculations. And then the second main result is basically the same thing, but now with strong convexity. So if you add strong convexity, then the picture changes totally. The the worst lower, the largest lower bound you get still goes to 0 geometrically fast, or exponentially fast. So you have this factor here which is smaller than 1, and it goes down with the case power of that. And so this is just a byproduct, because in the strongly convex case, this term here dominates the norm, and that's by a constant factor, and then that's just it. So you also see that if u goes to 0, this lower bound here totally deteriorates and doesn't tell you anything. And I think if mu goes to 0, this q goes to infinity, and this small q here goes to 1. So you lose any contraction or any reduction in the iteration if mu goes to 0. Okay, and there's the question that said, can you prove the last theorem without x0 equals 0? Okay, yeah. Somehow. Otherwise, just consider f of x minus x0. As new function g of x. So just translate. So if you have, for some function you start at some x0 is not 0, you could just shift the argument around by x0 and consider the shifted function as your original function. And then applying the full algorithm, the algorithm to the starting value x0 for the first function, you could as well apply the algorithm to the shifted function, but initialized at x0. That's totally the same thing. So, and of course, we could have, if you really insist that we should write it down, I think it's not it's not fun to do. But what you need to do is you consider a different annoying function actually really shifted by the values x0 here. And then most things hold true, but what is not true anymore is this is not like this anymore, but what is true is that the difference of xk and x0 only has entries in the first k, only has non-zero entries in the first k components. So everything is just shifted. It's just shifted. Also the minimizer, this x star, got shifted by x0. So here in these terms, this minus x0 here and minus x0 there just cancels out again, and the sums stay exactly the same, and really there's not much changing here. Yeah, so but maybe you're aiming at a different point, and this is so that this argument really relies on the starting point actually. If you start somewhere else, things may be more difficult, but where to start? Coming up with the good initialization, which works very good for all problems, I think it's basically as hard as solving the problem anyways. So, of course, for all problems, the best x0, the best starting point, would be x star, the solution. Because if you start on a solution, the gradient method would just get stuck there, because the gradient as a solution is 0, and so you start there, you stay there, you're optimal from the beginning. And that's the best initialization which you can have, right? So, but guessing anything good, which is better than starting at 0, I don't know of any tactics which could do that, actually. Yeah. So that's a good point, of course. So we all what we did here is in the case of convex functions, and this is for one reason why we did this in the convex case is that it's actually really we're able to prove something. So how does help us to study the loss functions in deep learning? That's I would say it's not totally clear. So, but one thing is clear: minimizing non-convex functions is of course not simpler than minimizing convex functions. So all the lower bounds which we derive here also apply to the non-convex case in general, because the problems may just be much harder. So these lower bounds here tell you that in the non-convex case you will not be able to beat this here uniform. It's just impossible, because the convex is a special case. But smoothness, I'd say, so the loss functions are not always smooth. but you can always smooth them out. So I'm not really sure if the non-smoothness is such a big deal, but it's still I'm totally not sure, because well, you're right. Usually in neural nets you have this rectified linear unit which has a kink, so it's not differentiable. But it seems like theoretically, practically it doesn't make a difference, but I'm not so sure about it. So then there's another argument, but I think this is not totally true. So one could argue that many functions which are non-convex look convex in the neighborhood of the minimizer, but that's not true. It's unclear for neural networks, I'd say. So, but if it would be the case, so if you consider you have so where do we have some like a convex function here, non-convex function? I don't know. So you could consider a non-convex surface, like so, a non-convex surface. So here it's a curved surface somehow. But if the minimizer lies in the bowl like this, then around this, in the minimizer of the bowl, the function is locally convex, and then everything is locally like it is here. So if you start in close enough to a minimizer, then this asymptotics would apply. But here comes the catch. It's totally not clear whether or not minimizers in the case of deep learning, are in points where the function is locally convex. And I would say recent evidence in the recent years more or less points to the opposite. So that's actually pretty recent research, and it's really unclear if it is like this. But it's hard to prove. But what people argue is, so in deep learning, you always use so many parameters that the problem is vastly overparameterized. So you have much more parameters than you need to fit your data exactly. So in many cases, it's like the set of minimizers is more than a point. It's actually very, very large. There are many, many minimizers, and people argue that it may well be that the set of minimizers may look like this. It's a lower dimensional manifold as part of a higher dimensional space. So, and of course, so this sheet of paper would now be the space of all parameters, so probably a billion dimensions. But the set of optimal parameters may still be a kind of a manifold, a curved line or a curved subspace of this very, very large dimensional space. And so this may be the set of minimizers. And then if you now consider level lines, so this is where the function is as small as it can be. The level lines may then look like this, going around here. This is here the function is a little larger. Here the function is a little larger again. So it may be that the loss function looks like the valley around a river in the mountains. So you have a valley. Here down here flows some river. It's flat down here more or less, and in this direction it's going up. But since the river here is now curved, it's really like that the function at this point, it's not locally convex around this point here. So it's not like this point has a neighborhood on which the function is convex, because it's this kind of this curved nature here. This may be how the loss landscape in deep learning actually looks like. And this would also, but to me, so it's recent. I think it's just something which appeared in the last 2 years at most. I think I first heard it 1.5 years ago. But if it's now then the case, then it's really unclear what the convex theory tells us, more than that the non-convex case is at least this hard. Okay, but it gives you let's turn it into a positive result. It turns if you can come up with a method which works on one specific problem, which may not be convex, like the error goes down like 1/k squared, then you're very good already. Then it's you're above the first benchmark, one could say. Or if you can come up with something which converges geometrically, then it's as good as it can get, I guess. So this, you can turn this into a positive thing. So this gives you a benchmark. If you can come close to that, then it's already very, very good. Okay. So if you have further questions, keep asking. I try to answer them as fast as possible. And otherwise, we have our next lecture tomorrow. And what you're going to prove there is we're going to analyze, it's from the other side. So now we proved the lower bounds, and next lecture we're going to prove upper bounds for some algorithms. We're going to prove that there's a specific method, and namely the gradient method, fulfills an upper bound, so it's better than something. But unfortunately, in both cases, both in the case of smoothness and smooth and strongly convex, the upper bound will be much worse than the lower bound. Not only by the constants here, but also by the asymptotic. So what we're going to see is that the gradient method cannot live up to this expectation here, that the error can go down like 1 over k squared. And also in the strongly convex case, we will see that the gradient method will give geometrical convergence, but with the worst number here. So it's another number smaller than 1, but it's larger than that one. But the good thing is, I think it's also the same lecture, right? It's also the same lecture that, no, it's not the same lecture. And then the beginning of the next week, we see that there are actually simple gradient methods which come close to this, which do have a 1 over k squared here. The worst constant, okay, but it's still 1 over k squared. So that will be the first lecture in the next week. Okay, so that's it for today. 20 minutes early, but I think that's fine. In case you have more questions, just ask, and then otherwise we meet again tomorrow. Okay, so see you.